Okay, we're trying to understand how to avoid the overfitting problem in decision trees, because decision trees are something that gets very quickly overfitted. The moment you have a lot of nodes in the tree or lot of levels in the tree, I mean, if the tree depth is too much, immediately you can say that. So if this is the tree depth is given as what is the distance of the leaf node, or what is the maximum distance of the leaf node. So for example, this is also a leaf node, so the distance is 1, but this is not the maximum distance from the root node to the leaf node. So the maximum distance is from here to here, and then from here to here, here to here. So the maximum distance here is 1, second hop, third hop. So if the depth of the tree is too much, let's say 15 or 20, something like that, then your decision tree is not going to work very well, because it is going to overfit with the training data set. So for that, what we realized is we have to, when we increase the depth of the tree, the training error at some point will become 0. But at the same time, if you go with the test error is going to increase. It is going to increase like this. Initially it is going to decrease, then it is going to increase. So your test error is going to increase, even though your training error is at some point it is hopefully 0. So that's why we may not want always to use the training data set. And secondly, we also may not want always a tree of very high, too much deep trees. The moment the tree depth is too much, so let me write the causes of overfitting in decision tree as a summary. Causes of overfitting in decision trees. So the first cause is tree depth is a measure of complexity of the tree. So too much depth means we are overfitting. Second thing is, if the tree is having too many leaf nodes, so this is also a cause of overfitting. If the tree is having too many leaf nodes, it means that the complexity of the tree is also more. So these two reasons we have to avoid always. So that's why we went with. So there are two. One second. Two different algorithms for picking a simpler tree. One is early stopping, which means you don't grow the tree very complex. So if you don't grow the tree too complex, then obviously you're not doing any overfitting. The second thing is simplify the tree after it became complex. So you grow the tree as much complex as you want. So let's grow like this. Now what you do is you cut down the tree. This is more like a gardening. You allow the tree to grow, then you do the gardening step. What you do in the gardening, you prune the tree. For example, if you remove this, let's say the test error, let's say the test error improves by deleting this node. Because if the tree is very complex, obviously the test error is very large. So it is on the U side. So the test error is given by this kind of a curve. If you grow a very complex tree, the test error is somewhere here. So what you do is you keep on removing some of the nodes wherever the test error is improving too much. So for example, if you remove this, the test error is decreased by 100, versus if you remove this node, the test error is reduced by only 50. Which one do you take? The one which is reducing the test error more. You pick that node and remove that remove that branch, cut that branch away. If you keep on cutting like this, at some point hopefully you'll reach here, and you'll nowhere you'll be able to no more cut down any part of this tree which will decrease the error, because you keep on cutting down the branches. At some point you already reached the minimum point. Now if you cut down any more, you are only going to increase your test error. So until that point, keep on cutting the nodes from the tree. Is this point clear? How do we prune the tree?
Yes.
Vidya, are you clear?
Yes, Sandeep.
Okay. So there are two ways. One is early stopping. So for early stopping, you can either limit the depth of the tree, which is a measure of your complexity of the tree. Then you can also limit the you can also use the classification error to limit the depth of the tree. And finally, you can also use you can also say, if my leaf node or the node in which I want to split the branches again, if that node is having too small number of data points, let's say if it is having less than 10 points or less than 50 points, you define the criteria. If it is having less than those number of points, stop building the tree. So that's how we can use any of these early stopping. Now that's what is the summary here. So the number one of early stopping is stop splitting after a certain depth. What does it mean? You don't go beyond a specified depth. Let's say if you say depth equal to 5, do not grow the tree more than depth equal to 5. At depth equal to 5, you stop growing the tree. But we went to some example where if we stop at some depth, it is too much short-sighted, because if we stop this tree at depth equal to 1, the classification error is going to be 0.5. If we keep on growing the tree after this also, then classification error becomes 0. This tree we have already seen yesterday, Friday. So in this tree, if the classification error is going down too much, then we cannot if we stop at depth equal to 1 itself, we'll not be able to know that if we grow the tree to next level, we will be able to solve the problem very easily, or we'll be able to classify very perfectly. That part will not be will just be blind, because at depth equal to 1, we only know that the classification error is equal to 0.5 or 50% error. We do not know what happens next. Only if we grow the tree to the next level, we'll be able to able to understand that at depth equal to 2, it is doing good. So that's why early stopping criteria 1 as well as early stopping criteria 2, even 2, because that criteria 2 is also saying the similar thing. If your classification error is not improved, stop growing the tree. In this case also, the classification error is not growing. I mean, not improving. So since it is not improving, if we stop it at depth equal to 1, it will be too much short-sighted for us. So what we should do is, pruning is always the best criteria that is available to us. If pruning is not possible because of whatsoever reason, go with early stopping criteria 3. 3 is much more better, because if you are saying each node is having too few data points, do not split, it is going to work very, very well in practice. Is this clear about all this early stopping criteria? Once again, yeah, this 3. Are you clear with this early stopping criteria? We already went through, but
Yes, sir.
once more I'm going. Vijay, are you also clear?
Yes, Sandeep.
Okay. So one thing I noticed is I'm not getting any questions these days. Is there any problem? Or is it because decision tree is very easy, so you're not getting any questions?
No, it's pretty easy to understand. Not easy, but you're explaining in a very logical way, so I understand it.
Okay. Okay, cool. So where are we? Pruning. So unfortunately, pruning is not something that is supported in Python, but we'll still go ahead and understand the theoretical aspects. It's not supported in Python anymore. So we can use random forest instead. So random forest is a much better technique than tree pruning. That's why pruning is no more supported in Python. In fact, it is not supported since its inception, because they have already got a better alternative, which is random forest. We'll get into random forest. Random forest is nothing. So let me give you an intuition. So what is a forest? It's a collection of trees. Is it right? Forest is nothing but it is having a lot of trees. So what we do with the random forest is, we know that if we grow the tree too large, if the tree complexity is too high, if it is too complex tree, then we are just overfitting the data, and we do not want to overfit the data. And so because of that, we are doing all this pruning and all those things. Instead of pruning, what if the tree is using, let me see, instead of pruning, growing the tree too complex and then trying to cut down the tree, just like you are doing in the in your garden, instead of doing like that, what if you develop, so let's say you have 50 variables. Just because you are having 50 variables, your tree is going to be too deep. But what if you randomly select 2 variables out of this 50 at a time, and then using only these 2 variables, you build one tree. Okay. Once again, out of these 50 variables, select 2 variables, build a tree. Which means for 2 variables, you'll not get too much of deep trees. You'll get only like this. Again, from these 50 variables, again select another 2 variables and create another tree. Again, select another 2 variables and create another tree. Maybe this time the tree will be like this. Again, select another 2 variables, create another tree. How many times you do? Maybe thousands of times, or tens of thousands. If you do like this, each tree is going to predict one class. Now, which class you should predict as a random forest, as a forest as a whole? You should predict the one that is predicted by the majority of the trees. Are you clear? This may look like a little confusing, and you may not understand why it is worthy to do like this. But my question is, so my answer for this is, this guy is a specialist. This guy is specialized in 2 variables, which are V1 and V2. This guy is a specialized person or a specialized tool that we have built for V3 and V4. These are another 2 variables. So there are specialists for each aspect of the data. Now, if you have specialists for each aspect of the data, if you combine all of them, you're going to get a better result. So for example, it is more like your, if you know about IMF, do you know about IMF? What is IMF? International Monetary Fund. So these guys are going to write down some economic policies that has to be followed by the person, by the countries who take money from the IMF. So let's say if US is going to take some money from IMF, so the moment US takes some money from the monetary fund, International Monetary Fund, then there are a set of economists who are going to dictate the rules. If you take from money from us, you have to, your country's economic policies has to follow these set of rules or these set of guidelines. That's how IMF kind of organization works. Okay. Now IMF is going to have, let's say, 100 different economists. Now each economist, so economics is not a very simple subject, right? There are a lot of subsections or sub topics in economics. Each of these 100 economists is a specialist in one particular topic. Now, if you combine all those specialists, then you are going to get a better results than having one specialist of all, one specialist for all the subjects in economics. Do you agree or not? Did you get the the example that I gave? It's more like you have 100 different economists, each one is not a specialist in all the topics of economics. Each one is a specialist in one particular aspect of economics. Now, if you combine all of them together, then you're going to get a better result. Are you clear, Vijaya and Abid?
Yeah, Sandeep.
Vijaya?
Yes, Sandeep.
So the idea here is in random forest, the idea is the crowd is going to outperform one single individual. The knowledge of the crowd is more than the knowledge of an individual person. So we're going to look at that one also. Okay, random forest. It's very interesting actually, because you'll never have realized the power of crowd. We are going to use that crowd, the advantage of the crowd. So it is used, this kind of concept of crowd having more knowledge than an individual person, or crowd is more specialized than an individual person, is used in many areas. If you think of, I don't know how many, if you know about crowdsourcing, do you know those words? So for example, yeah, anyone?
Oh no, I heard of those words.
Yeah, the idea is if you have, let's say you want to build a small, what do you say, you have a personal project. Let's say you want to build a solar powered water heaters for your village or for your community, whatever community you're living in. So what you can do is, instead of putting your own money or all your money, what you can do is, there are some websites nowadays which will ask for where you can put your ad. It is more like, it is an online ad where you can ask for crowd funds. If you go for, I don't know if you went with Kickstarter. So if you go for any kickstarter.com or anything, you can see these guys have a idea which can change the lives of many people. Or these guys are going to have some idea which can be utilized for creating a company. So for example, let's see something interesting. Let's say these guys are having some ideas about how to, some ideas about how to make a film. For each such film, you can create a ad like this, and you can ask for how much you can contribute. So everyone is going to give, let's say, $10 or so, but at the end, this guy is having $3,200. So the crowd is funding this project. Each one may give only $10, but at the end, you are getting some good amount of money for you to continue with your project. Similarly, in the random forests also, each tree is going to contribute a little to the final goal of predicting something. But finally, since each tree is a specialist in something, but not a expert in everything, this tree is not an expert in all the variables. There are 50 variables, but definitely for 2 variables, this is an expert. For another 2 variables, this is another expert. So each tree is an expert in something, but not an expert in everything. If you combine all these experts together, then you are going to get a better result than any other single tree. That is the idea of random forest. Now, because it is having only two variables, this tree is not going to grow too much. So each tree is very least complicated. The complexity of the each tree is not that much. It's very less. So that's why in Python, what they did is they removed this. I mean, they did not create any support for pruning because they realized that this is not really important. But we are still going to address this concern of how we are really going to understand. I mean, we are going to understand what is this tree pruning, how to do it. But in Python, we cannot show it. Is that fine? Because we have a better technique. I'm going to explain the pruning only because this is an important topic for if you go for any interviews. Is that clear?
Yeah, Sandeep, it's okay.
Are you clear how random forests work in the first place? We're going to go into random forest as well. This is not it. Whatever I told is only the introduction of how random forest work. But we're going to address this concern in detail more. So that is about the tree pruning and random forests. Now let's understand the theoretical aspects of tree pruning. Obviously, like I said, this is not supported anymore in Python, so we don't have to worry about that. We'll worry about the random forest aspect. Now, there are two approaches for picking the simpler tree. This we already saw this. One is do not grow it complex. Another is grow it complex and then cut down. Both are a little bit complementary steps. One is you grow the tree as much as possible, then cut down. Another is don't grow the tree complex also. Why do you want to care about complex tree and then cutting down? So each is a different branch of study, but in general, pruning is much more efficient and much more reliable method than early stopping. Early stopping is not such a great one. This is a great one. So given a chance, if someone asks you what is the better technique, is it an early stopping or pruning? I would anytime go with pruning. Unfortunately, like I said, it's not available in Python, but if it is available, definitely go for pruning. Now, how do you prune? You have a complex tree. Look at some nodes and cut down some of these. Let's say you cut down this, you cut down this, you cut down this. You have to pick some nodes or branches which you have to cut and make it as a simpler tree like this. So you can see this is a very, very complicated tree, and you cut down some branches and got this kind of a tree. What you did, I think in this case, all this is cut down. Only this above part is there. Okay. Now, if you have a very complex tree, your complex tree may be somewhere here or somewhere here, somewhere on the right side of the true error. So what you need is a simple tree, which is at this point. So if you don't do an early stop, you are already at this right side of the tree. Right side of this U curve. So what you have to do, you have to keep on cutting. Maybe if you cut one branch, you are here. Another branch, you are here. Third branch, you cut, you are here. Likewise, you keep on cutting. Your error will come down. At some point, hopefully, you'll reach here. And at this point, if you even cut more, then what happens? Your training error again increases. So that is the point where you should stop. So again, we went through these things, I believe. But which tree is simpler in this case? Is it this one or this one? Obviously, the second one is much more simpler. One thing is here the maximum depth is 1, 2, 3, 4. So you start from the first node, root node. You keep on counting the number of hops. First hop, second hop, third hop, fourth hop. Now when you are hopping, try to choose the branch which is having the having the maximum depth. Do not choose this branch. This branch is saying only two hops. What you should do is from root node, whichever leaf node is having the maximum depth, that is going to be the max depth of the tree. So for example, in this case, it is only 2, 1 hop, 2 hops. 2 is the depth if you go this branch. If you go this branch, 1, 2, 3. Again, this side also it is 3. And if you go this side, 1, 2, 3, 4. So this side it is 4. And this side also it is 4. This is 3, 3, 2. If you go this side, 1, 2, 3. So these are the depths for each leaf node. Whichever leaf node is having the maximum depth, that is the depth of the tree. So for this tree, the maximum depth of any leaf is 4. So for this tree, you can say 4 is the depth. Depth equal to 4. So this tree is obviously complex because it is having a higher depth. And this tree, it is having a depth only as 2. So which tree is simpler? Always the right one. The right one is the simpler here. But here, we already saw this one also. Here, the depth is only 2. Why? From here to here, 1 hop. From here to here, 2 hops. 2 is the depth. For each of these nodes, depth is same. 2, 2, 2, 2. And here also, the depth is 1, 2. Here it is 2. Here it is again 2. So maximum depth here is 2. Maximum depth here is also 2. But which tree is simpler? Again, the right side. Sorry?
Less leaf nodes tree.
Yeah, less leaf nodes. Again, here also the right side one is simpler because we are just here having the same depth. But what we can do is, instead of taking depth as the complexity of the tree, we can take the number of leaf nodes as the depth of the tree. That way, we will not have any ties like this. That way, we will have lesser number of ties. So in this case, the leaf nodes of the right side one is lesser. So obviously, you should say that this one is simpler. So the simplest measure of complexity of the tree is number of leaf nodes. If you are having too many leaf nodes, say that it is having, if it is having too many leaf nodes, then say that the complexity of the tree is more. Now in this case, how many leaf nodes are there? 5. These are all leaf nodes. And in this case, only 2 leaf nodes. So leaf nodes are determined, denoted by L of T. So L of T1 is 5. In this case, it is 5 leaf nodes. L of T2 is 2 nodes. So whichever is having lesser L of T, you call it as a simpler tree. So this is having lesser leaves. So you call the right side one as having a problem. Having a simpler tree. Is it clear so far? So,
Yeah, Sandeep.
so what we want to do is we want to prune the tree. We want to cut down the branches of the tree, and at some point we want to get a least error. Is that what we want? We want the least, sorry, we want to have a least error, test error. We want to cut down the tree and get the least error, and at the same time we also want a minimum complexity tree. Okay, we want both of them together. So what we want to do is we want to balance how well the tree fits the data. What does it mean? How well the tree fits the data means least error. If the error is less, then the tree is fitting well. If the error is more, the tree is not fitting well. This, how well we fit the tree, is what we want to balance with, along with the complexity of the tree. The tree should not be too much complex, as well as the tree should fit the data very well. We want to balance both of them together. So that's why what we are defining is, we are defining some measure of fit. Measure of fit means classification error, this one. And we want to also balance this with the complexity of the model. For example, number of leaf nodes or depth of the tree, some measure of complexity you have to use, plus the classification error you have to add. That is going to be your total cost, and you want to minimize your total cost. Is that right or not? You want to minimize the complexity of the tree as well as the measure of fit, which means the error. Minimize the error, minimize the complexity. If you do both of them, then you are done with your decision tree pruning. Are you clear or not? What is your total cost of the tree? The cost is now determined by how much errors you are predicting, how much error is in your prediction, as well as what is the measure of your complexity of the tree. The error should be minimum, and also your measure of complexity, which means your tree should also not be too much complex, because otherwise it will not fit well on the test data. So minimize the complexity as well as minimize the error. If you do both of them together, then your cost of the tree will go down. So that's why we're defining another term called total cost, and the total cost is nothing but the measure of fit plus measure of complexity. If you remember, we did the similar thing in lasso regression. In lasso, what we added? Lambda times of modulus of beta. This we added to sigma a square and called it as error. Now we are, instead of calling it as error, we are calling it as cost. We are saying total cost. Are you clear with this? Ridge regression, whatever we did, is same as this one. This sigma a square is nothing but measure of fit. This modulus of beta, lambda times of modulus of beta, is nothing but measure of complexity. How does it work? For example, if lambda equal to 0, what happened? Your beta values are too high. You are not balancing the beta values. If lambda value is too high, what happens? Then beta value is very low. This one will be very low. This sigma e square will be high. Are you clear?
Yes, Sandeep.
So for example, if total cost is fixed, let's say it is 10, and let's call it as x and y. This is x and this is y. So for x plus y to be always equal to 10, what you should do? Either increase this one. If you increase this one, what happens? Automatically this one will decrease. For example, earlier it is 5. Now you increased x value to 6. What happened? Automatically, for this sum to be always to be equal to 10, this value will get decreased. Earlier it is 5, y is 5. Now it will go back to 4. If you increase one quantity, the other quantity will be reduced. Now if you increase y, x will get reduced. Yes or no? Vidya, are you clear?
Yes, Sandeep.
So what you're doing is you're adding this kind of a tuning parameter. If you increase this, then this part, to offset this overall cost, this beta will get decreased. If you increase lambda, beta will be decreased. If you decrease lambda, beta will be increased, because your total cost is always constant. Are you guys clear or not?
Yes, Sandeep.
This is another way of looking at the lambda. This is not lambda, but in our ridge regression, we mentioned this as alpha. But whichever it is, if you increase that quantity, the beta values will decrease. If you decrease that quantity, beta values will get increased. Is that intuitively clear?
Yes, Sandeep.
Okay. So that's what we are going to do here as well. So we call this classification error as E of t or error of t. Number of leaf nodes are L of t. And we are going to add some tuning parameter lambda. Why are we adding this lambda tuning parameter? Because if you increase lambda, if lambda increases, what does it happen? If lambda is, or let's say lambda equal to 0, what happens if lambda equal to 0? If lambda equal to 0, then regardless of number of leaves in the tree, even if you have a lot of leaves in the tree, the cost is unimpacted. So what happens? If lambda equal to 0, then you are going to get a full decision tree. There is no pruning at all. Pruning will never happen. Yes or no? If lambda equal to 0, L of t doesn't matter. It doesn't matter what is the value of L of t, even if it is 50 or 100, that value multiplied by 0 will always be 0. So regardless of the number of leaves in the tree, the cost is unimpacted, which means you are not going to prune anything. But so no pruning. If lambda equal to 0, no pruning at all. If lambda is too high value, let's say it is infinity. If lambda equal to infinity, your cost cannot be always infinity, right? Your cost cannot be always very large. Your cost cannot be too large. So because of that, number of leaves in the tree will become 0 to offset that. Are you clear or not? Your cost cannot be too much. So if L of t is infinity, too large value, to offset that, number of leaves in the tree will become 0. So because of that, what does it mean? Only root node exists. Are you clear or not? If lambda equal to 0, there is no pruning, which means tree grows very large. The complexity of the tree is very high. If lambda equal to infinity, then number of leaf nodes will become 0. just to offset this one, because your total cost cannot, your total cost is supposed to be minimum. It cannot be infinity. So to offset that, what happens is all the leaf nodes will get pruned. If all the leaf nodes gets pruned, then only root node will exist. Are you clear or not? Vijaya, Abid?
Yes, Sandeep.
Yes, Sandeep.
If you have any questions, ask me now. Because, you know, if we go further, you may get confused again.
No, I'm clear. Thank you, Sandeep.
Okay. Vijaya, are you clear or not? You are also
Yeah.
clear?
Yeah, I'm also good, Sandeep.
Okay. Okay, then let's take a break of 5 minutes. We'll come back at 7:30 and understand the remaining concepts of tree pruning. Okay. Let's come back at 7:30.
Sure, Sandeep.
Is everyone back?
Yeah, I'm back, Sandeep.
Yeah, I'm back, Sandeep.
Okay. So if you consider this as a variance bias trade-off, so if you increase the, so lambda is nothing but it is going to, so it is going to do a variance bias trade-off. How does it do variance bias trade-off? So variance, so bias increases when your lambda is equal to 0. If your lambda equal to 0, if you are not doing any pruning at all, then you are fitting your model to you're fitting your data. Sorry, I'm sorry. You're fitting your tree to your data too much. So there is a lot of bias. Again, if I'm sorry for that. I'm thinking in a wrong direction. I'm sorry. So if lambda equal to 0, what happens? If lambda equal to 0, the number of leaves will become too much. If number of leaves equal to too much, then the complexity of the model is too much. So if the complexity of the tree or any machine learning model, if the complexity is too much, then immediately you can recognize that the variance of the model is too much. Is it clear? Similarly, if lambda equal to infinity, then the number of leaves will become 0. It is a very, very simple model. Always remember, simple models correspond to high bias. Because your model is biased because having only one root cannot give you anything. That's why you are saying the model is biased. Are you clear? I'm sorry, I was not giving a right approach initially. Are you clear, or shall I explain again?
No, I got it. So basically, if lambda is 0, then that means the complexity model is too much because we're getting a full decision tree. So that means variance is also a lot.
Exactly. If the full decision tree is coming up, then your complexity is too much. The moment you say the complexity of the model is too much, then immediately you can say that variance is high. Because, for example, you can consider this, always compare with the linear regression. That is the advantage of learning linear regression. So let's say this is a high complex model. x1 square and x2 power 4. This is a high complex model. The moment you say the complexity of the model is high, what happens is just by changing a little of x2 or x1, one of the variable, if you change a little, then immediately you'll see a lot of variance in the y hat. So the moment your model is having a lot of complexity, immediately you can say that variance is high. If you take the reverse of this, the moment you say it's a very simple model, what is that? For example, one of the simplest model in linear regression is this one. Y hat equal to beta naught. Very simple model, but it is very biased. You cannot always have beta naught as your y hat model. It's a very biased model. So too much simplistic model corresponds to bias. Too much complicated model corresponds to variance. Always remember this part. Now, if you consider this with the tree, decision tree, if lambda equal to 0, no pruning, it means that the model is too complex, the decision tree is too complex. It means you are having high variance. If lambda equal to infinity, it means that only root exists in the model. It means that high bias. So this total cost, what it is doing is, it is trying to balance between the model which is having high variance versus a model which is having a high bias. High bias versus high variance. It is going to take a balance between high bias versus high variance. So that is how this model is going to have a better variance bias trade-off. And that is what is very important. I said in the beginning of the machine learning classes, I told you that all we are interested is having a better variance bias trade-off. So pruning is one such example. When you are doing a pruning, what you're doing is you're trying to balance between variance and bias. You're going to get a moderate bias and moderate variance model. Is that clear? This is very important. If you understand this, you know, the remaining of the machine learning I can teach very easily. That's why I'm pushing more.
Can you repeat the last sentence about the moderate bias and moderate variance?
So what is your total cost in when you're doing pruning? Your total cost is a combination of error plus some lambda times of leaf nodes. Now this lambda times of leaf nodes is going to give you a better variance bias trade-off. Why is that? If lambda equal to very small value like 0, then you are going to have high variance. If your lambda is equal to infinity, you are going to have high bias. Now, if you choose a lambda in such a way that you do not have too much of variance as well as too much of bias, then you are going to get a trade-off between variance and bias, which means you are going to get somewhat moderate bias, somewhat moderate variance, right? Yes or no? If you select a value between 0 and infinity somewhere, at some point you're going to get both variance and bias as a moderate values. It's not low, bias is not low, variance is not low. At some point what happens? Let's say lambda equal to 10 or 15 or something like that. At some point of lambda, neither variance is too high nor bias is too high, which means you are going to get a moderate variance and moderate bias. You are going to get a variance bias trade-off. At that point, you fix the lambda, which means this formula of total cost is going to give you a better variance bias trade-off, provided that you chose a better lambda. Are you clear or not?
Yes, Sandeep.
So lambda is your tuning parameter. You have to tune it yourself. Now, how do you tune it? We already know this. The answer of this we already know. What you do? You split the data into train, validation, test data sets. On train data set, you train the model. On validation data set, you validate if you are given lambda, whatever you provided, that lambda is correct or not. Whichever lambda is giving you the minimum validation error is what you have to choose. You try out various lambda values, and wherever you find the lambda value as minimum, lambda value that is giving the minimum total cost, that is the lambda value you have to choose. Yes or no? It is based on train, validation, test data sets. If you use those 3 data sets, train the model and choose one lambda value, let's say lambda equal to 0. Train the model on train data set. Then on validation data set, find the total cost. You will get some total cost. Again, choose another lambda value. train the model and train data set, get the total cost on validation data set again. For every data set, such data set, for example, let me write it. Tree pruning. What you do here? Cost equal to classification error plus lambda times of L of t. How to choose lambda? Try out different values of lambda for each lambda value. Train the model, which means decision tree model, on training data set. When I say training, train the model, you have to create a decision tree and then prune the tree as well using this lambda. Test or get the validation error on validation dataset. Now on validation dataset, once you do it, once you get a validation error, find the lambda, or let me write it as keep on doing steps 1 to 3. Steps 1 to 3 for different lambda values. Just keep on doing the same thing. Try out different lambda, train the model, again try out the different model on different lambda and get all these validation errors. Then choose which lambda? Choose the lambda which is giving least, which error, train error or validation error? Always validation error. Least validation error. Are you clear, Vijay? How to choose this lambda?
Yes, Sandeep.
Always whenever I say tune this parameter, tuning means you have to find out what is the best value. Machine learning will not find you the best value. You have to find it yourself. Whenever I say you have to tune this parameter, you have to do the same thing. If it is lambda or whatever alpha or whatever the name is, try out different lambda values on validation dataset. Whichever lambda value is giving the least validation error, that is what you have to use. Hope this is clear. Hope this is clear. Any questions so far? Okay. So how to prune? So you have to use the total cost to simplify the trees. That's what we have realized. Then to do the pruning, always start the pruning from the beginning, from the end of the tree, bottom of the tree. That's what I wrote here. Always do the pruning from the bottom of the tree. Do not take this node and then try to prune this. If you prune this, then there is no tree at all. If you remove this, then this entire tree is gone. Do not do that. Always do the pruning from the end of the tree. Start from one of the end. Maybe this one, try this one, try this one, like that. Do not try this one before you try this one. Only if you cut down this one, this term branch, only then consider this for pruning. Okay. So what are the initial candidates for pruning? Either you can try this one or you can try this one, because these are the bottommost branches which you can try out. You cannot try out this income branch because below this income branch there is another branch. This is not the bottommost branch. So do not try this income branch. Similarly, you cannot try this credit branch. This is not possible. This is not possible initially. So what are the candidates? Either this one or this one. Now what to do for pruning? Try to remove this term from the tree. If you remove this term from the tree, then you have to find out what is the cost, if what is the overall cost of the tree if you remove this branch. How do you know? For this tree, let's say the error is 0.25 and the number of leaves are 1, 2, 3, 4, 5, 6. 6 is the number of leaves, and the tree is having an overall error as 0.25. 0.25 is not the error only for this branch. 0.25 is the error for the entire tree. Error for entire tree. Do not consider only this one. Now, what is the overall cost? Cost is nothing but error plus lambda into L of t. Now, in this case, we chose a lambda as 0.03. Let's say I chose the lambda as 0.03. What is the overall cost? 0.25 plus 6 into 0.03. 0.43 is the total cost. That's what he has mentioned here. Are you clear so far? How this error came up? Error is the error for the entire tree, classification error. And cost is nothing but error plus lambda times of L of t. And lambda, let's say I chose 0.03. That is the initial lambda I have chosen. Are you clear so far? Now let's say I prune this one. So this cost is before pruning. Let's say I prune this one, this term branch. What happens? If I prune that, I replace that with some leaf node. Leaf node is nothing but the majority class. Let's say the majority class here is safe loan. If I prune this, how many leaf nodes are there? 3 plus 2, 5 leaf nodes are there. And let's say the error got increased to 0.26. Okay. Now what is the total cost after pruning? 0.26 plus number of leaves, which is 5, into lambda. Lambda is 0.03. So your total cost got decreased from 0.43 to 0.41. Now the new total cost is 0.41 after pruning. Are you clear so far or not?
So we're keeping the lambda constant.
Yes, for now let's assume that lambda is constant.
Okay.
Let's assume that we picked one lambda. If you remember, if you go back and see your algorithm for choosing the lambda, you choose one lambda and do the training. Now what we are doing is still training. Pruning is also part of the training. That's what I mentioned, right? For each lambda value, train the model on the training data set. We're still training. Training means you grow the tree to the maximum extent and then prune. Both of them together is a component of training. Are you clear, Vijay, now?
Yes, Sandeep.
Okay. Now, what you do here, before pruning, you calculated the total cost, which is nothing but 0.25 plus 0.003 into 6, which is coming as 0.43. So before pruning, our cost of the tree is 0.43. After pruning, our cost of the tree is 0.41. So what happened? Our total cost of the tree got decreased. So since our total cost of the tree is decreased, what you do? You go ahead and prune the tree, prune this branch. Then again, you have to again prune. I don't know if this is enough for pruning. Maybe I have to prune one of this, either this one or this one. I have to go ahead and prune. Maybe if I prune again, I may get a better cost again. I don't know. So I keep on doing this. Decide if each of the split can be pruned. Which of the split can be pruned? This one can be pruned, this one can be pruned, but this credit cannot yet be pruned because this is at the second level. This is not at the bottommost layer. So credit cannot be pruned. I can choose either term or income can be pruned. Now, which of these two can be pruned? Whichever branch is giving the best cost is going to be pruned. For example, if you prune this one and I got a cost of 0.39, and if I prune this one and I got an overall cost of 0.35, which one should I prune? Whichever is getting a least cost. If I prune term, I am getting a best cost compared to this one. So I have to choose the term. Are you clear so far or not?
I'm clear, Sandeep.
Okay. Whichever is giving you the best cost, prune that branch first. Do not prune the one that is not giving you the best cost. So that is the algorithm here. So start at the bottom of the tree. That's what I have mentioned. And traverse up. You keep on going up and apply this method, prune split, for each decision node. How to do that? First, initially compute the total cost. Cost is nothing but the current error of the entire tree plus lambda times of total number of leaves in the entire tree. From that you get a total cost. Now T smaller means what? After pruning, the tree is called T smaller. So let T smaller be the tree after pruning the subtree before M. Okay. Now, so once you prune the decision node M, then you call the tree as T smaller. Now compute the total complexity of the tree, which is called T smaller, which is nothing but cost of T smaller as error plus lambda times of leaf node, number of leaf nodes of the small tree. If the cost of the smaller tree is less than the cost of the original tree, then prune the tree to T smaller. The same thing, he has just given a mathematical notation. Are you clear with this algorithm? We're almost closing on. Just keep on removing the tree, pruning the trees, pruning the decision trees, decision nodes. So that is what is the summary. I'm not going into the summary, don't worry about that. But if you see this entire algorithm, lambda is fixed, like Vijay already pointed out. Lambda is fixed as 0.03. Now, for one such lambda, you keep on pruning and you got some pruned tree. For that pruned tree, what you do is you go and apply that pruned tree on validation dataset. That part is not given in the PPT, but how to choose the lambda? For one lambda, choose one lambda and do the pruning that is given in this PPT. Keep on pruning the tree. At some point, what happens? Your cost of the tree is no more decreasing. It will start increasing. If you remember this slide, yeah. If you see this slide, if you keep on pruning, initially it will get decreased. The training error will keep on decreasing. But at some point, if you keep on pruning, the training error will increase. So at that point, stop the pruning for that lambda. Now, for that lambda, give this tree to the validation dataset and get the validation error. Now you get some validation error. So for different lambdas, you get different validation errors. Again, plot another curve like this. At whichever lambda the validation error is minimum, that is the lambda you have to take up. Is that clear? Vijay, are you clear now?
Yes, Sandeep.
As part of the pruning, we don't consider different lambdas. We consider only one lambda and do all the pruning. And for that lambda, plot the validation error. If you do the same thing for different lambdas, you'll get the lambda which is having the least validation error. So that is how you can do the pruning. Any questions so far? Pruning is something that is very important. Unfortunately, it is not there in the Python. But the most important thing that you want to learn here is how do you do pruning, so that if someone asks you, you should be in a position to answer it at least. It's okay if Python doesn't support it. At least you need to understand the theoretical aspects of it, so that at least you are knowledgeable enough to answer the questions on pruning. So any questions?
No, Sandeep.
Okay then. So that's what I have for today. Any more questions, Abid? Do you have any questions? So we are almost closing on decision trees. Only thing is, we do not know how we can do random forests. That we are going to learn more. But for now, this is all we have for decision trees. We are definitely going back into random forests again. But for a single tree, this is all we have.
Is it possible to do like one example?
We'll be doing that.
Okay.
Python, we're going to do that.
Okay.
Only thing is we don't have time today. We'll look at it tomorrow. Okay. We have an example on, I already copied that, or if you want, I can show it now itself. The data set is called Iris dataset. In fact, on Iris dataset, I'm getting an validation error of 0. On Iris dataset, I'm getting a validation error of 0. That's what I'm getting. It's very, very powerful technique. The decision tree is very, very powerful technique. Even for Actually, Iris dataset, I am not getting very good accuracy on logistic regression. But if I do the same thing on decision tree, I was getting very, very good accuracy. I'm getting an accuracy of 1. You can see how good it is. If you want, I can tell it now. It will take another 10 minutes. Otherwise, I can show it tomorrow.
If we can do it tomorrow.
Yeah, that is good, right? So yeah, I'll take it tomorrow. Don't worry about that. We are going to work on examples. Do not worry about that. For every technique, we are going to solve one problem. Without solving, unless, you know, for example, pruning is not supported in Python. If that is the case, I am helpless. But otherwise, most of the cases we are going to go into the problem. Anyway, we are going to do the problem tomorrow. Other than that, do you have any questions?
No, Sandeep.
Great. So that's all I have for today. We'll catch up tomorrow again. Bye.